Random forest is a powerful method for regression and classification. We will next cover the conceptual foundations of random forests, but we need to start from a simpler method first. These simpler methods are called tree-based methods. The random forest method makes use of several trees when making its prediction, and since in graph theory a collection of trees is called a forest, this is where the random forest method gets its name. In other words, to make a prediction, the random forest considers the predictions of several trees. It would not, however, be useful to have many identical trees, because all these trees would presumably give you the same prediction. This is why the trees in the forest are randomized, in a way we'll come back to shortly. Tree-based methods can be used for regression and classification. These methods involve dividing the predictor space into simpler regions using straight lines. So we first take the entire predictor space and divide it into two regions. We now in turn look at each of these two smaller regions, divide them into yet smaller regions, and so on, continuing until we hit some stopping criterion. So the way we divide the predictor space into smaller regions is recursive in nature. To make a prediction for a previously unseen test observation, we find the region of the predictor space where the test observation falls. In a regression setting, we return the mean of the outcomes of the training observations in that particular region, whereas in a classification setting, we return the mode, the most common element of the outcomes of the training observations in that region. When we use lines to divide the predictor space into regions, these lines must be aligned with the directions of the axes of the predictor space. And because of this constraint, we can summarize the splitting rules in a tree. This is also why these methods are known as decision tree methods. In higher dimensions, these lines become planes, so we end up dividing the predictor space into high-dimensional rectangles or boxes. How do we decide where to make these cuts? The basic idea is that we'd like to carve out regions in the predictor space that are maximally homogeneous in terms of their outcomes. Remember, we'll ultimately use the mean or the mode of the outcomes falling in a given region as our predicted outcome for an unseen observation. So we can minimize error by finding maximally homogeneous regions in the predictor space. Whenever we make a split, we consider all predictors from x1 to xp, and for each predictor, we consider all possible cut points. We choose the predictor cut point combination such that the resulting division of the predictor space has the lowest value of some criterion, usually called the loss function, that we're trying to minimize. In regression, this loss function is usually RSS, the residual sum of squares. In classification, two measures are commonly used, called the Gini index and the cross entropy. You can find their definitions online, but the basic idea is again to make cuts using a predictor cut point combination that makes the classes within each region as homogeneous as possible. Let's look at decision trees on the whiteboard. Let's think about a classification problem where we have two covariates or predictors again, x1 and x2, and we have a bunch of observations in this space. Because it's a classification problem, each point will have a class associated with it, either number 1 or number 2. Let's add a couple of more classes here. The idea with decision trees is the following. We're trying to split this space, the predictor space, by forming regions that are maximally homogeneous. So let's say we happen to have many 2's here and just one 1 there. One option would be for us to split the predictor space here. If our x1 ranges from 0 to 10, this might correspond to a value of x1 is equal to 6. What does the tree representation look like? So at the top, we start from all of our data. We split the predictor space into two regions. In this region, x1 is greater than 6, so it corresponds to the right branch. And this part here, this region corresponds to a situation where x1 is less than 6. Once we've now split the space into two, we can proceed to make a further cut. So for example, perhaps in this region over here, which corresponds to this branch here, we might choose to make a cut here for a given value of x2. In the tree, we then introduce another branch. Let's say that the value of x2 here happens to be 8. And in this case, the cut is based on the value of x2. So we go to the right if the value of x2 is greater than or equal to 8. Otherwise, we go to the left branch, and so on. So we continue to build these trees. We continue splitting these regions by introducing cuts in the predictor space. We stop once we meet some stopping criterion. At that point, we should have regions here that consist mostly of 2's and 1's, say 2's here and 1's over here. How does a decision tree make a prediction? Let's say we have observed a data point here, which corresponds to a specific value of x2 and a specific value of x1. If this is a classification problem, which it has been so far, we first find the region where this data point falls. In this case, it's this particular region here that we're now highlighting in green. Because it's a classification problem, we find the mode of these observations here. They all seem to belong to class 2, and that's why our prediction for this point is going to be equal to 2. If we were dealing with a regression problem, we wouldn't have 1's and 2's as the outcomes, but we would have some other measurements like BMIs or incomes or something like that. To make a prediction in that setting, we would proceed just as before, but instead of returning the mode, we would return the mean of the observations in that region.